Okay, in this video we're going to do our first actual integral in spherical coordinates. Before we do that, I do just want to clarify. dv is rho squared sine phi d rho d phi d theta, in whatever order you want, but that's the order I suggest. I realized as I reviewed the last video that at one point I had been trying to write sine of phi star, and I think I had written sine of phi squared instead of star. Or maybe it was a star and it looked like a 2, but I think I wrote a 2 instead of a star. Did not mean to do that. I said the right thing, I think I may have written the wrong thing. So the rho is squared, but it's just one factor of sine phi. Okay, so I want to find the volume of the solid unit sphere. Now, if you know the formula for the volume, you know it's going to be 4/3 pi. That's kind of cool. And if that showed up as part of a larger problem, you could just use that fact from geometry. But here I want to actually do it by integrating in spherical coordinates. Okay. And I'll just mention that when we have a solid sphere, that's often referred to as a ball. So if the book is talking about, hey, you've got a ball or something like that, they're talking about a solid sphere as opposed to the surface of the sphere. Okay, so I'm going to set this up as a triple integral. Now I know that I'm going to just call this sphere S, so I would have the triple integral over S of 1 dv. But when I'm switching to spherical coordinates, that dv expands. So I'm going to have to figure out my limits of integration, but my integrand is going to become rho squared sine phi d rho d phi d theta. Okay. And now I need to figure out these limits. Now the solid sphere is a simple enough region, you might be able to just see by inspection what those are. But I'm going to walk you through my thought process for finding the limits of integration in general. We might not need these tools for this problem, but this will be a nice warm-up for some more complicated problems later on. So generally speaking, I'm not going to do an integral in spherical coordinates if I don't have rotational symmetry. So I'm going to, and I do for the sphere, have rotational symmetry. So I like to draw what I see as the intersection of my solid with an arbitrary theta half plane. So this is the z-axis, this is the xy plane, which is coming out towards us. And basically I'm going to see a half disk. Okay. And I'm going to see that in every theta half plane that I have because of the symmetry of the sphere. Okay. Now, I mentioned that I'm almost always going to integrate in this order, so that my theta limits of integration are the ones that must be constant. Now, in theory, that means that phi is allowed to be a function of theta, but like I said, I'm generally not going to use spherical coordinates if I don't have rotational symmetry. If I do have rotational symmetry, theta doesn't affect what I get. So my phi values are generally going to be constants as well. And then we're looking at finding rho as a function, in theory, of phi and theta, but realistically, almost always is just a function of phi. So on this picture, I'm going to draw in some constant phi rays. You might say, how did phi become a ray? Well, I know a constant phi surface is a half cone. But the intersection of a half cone with a half plane is just a ray like so. And so now I can look and I can say, okay, for each constant phi ray, I can see I'm in the region as rho varies from 0 to the rho value on the boundary of that half disk. But since this was the unit sphere, I know that that's 1. So rho is varying from 0 to 1. I can see that phi is varying from 0 to pi. And of course, if I want the entire sphere, theta is going to vary from 0 to 2 pi. Now, this is a simple enough example that you might have been able to say those were the limits of integration without drawing this picture. But I wanted to introduce this picture because that's what we're going to need in some more complicated scenarios. So now, let's integrate. We'll start with integrating the rho. So we're going to have the integral from 0 to 2 pi. Integral from 0 to pi, rho cubed over 3 evaluated between 1 and 0. That's still multiplied by sine phi, and then we'll have to integrate d phi d theta. When I plug in 1, I get a third, and when I plug in 0, I just get 0. So this evaluates to 1/3. That's a constant, so I'm just going to pull that out. So I've got 1/3 integral from 0 to 2 pi, integral from 0 to pi, sine phi, d theta. So that's 1/3 integral from 0 to 2 pi, d theta. I'm now doing the integral with respect to phi. An antiderivative of sine phi would be negative cosine of phi, and that's going to be evaluated between pi and 0. Let me clear some space. So that's going to give me 1/3 integral from 0 to 2 pi of cosine of pi is -1. The opposite of that is +1. Minus negative cosine of 0 is 1, and then we integrate d theta. So 1 minus -1 is just 2. That's a constant. Okay. So I've got 1/3, and when I integrate a constant, I just get that constant times the length of this interval, which would be 2 pi. That's going to give me 4 pi over 3, confirming that we do, in fact, get the correct answer for this problem. Okay, back for more in a minute.